Okay, I handed back the quiz. And are there any extra solutions? Let me see. Oh, it's a couple extras here. Oh, I'm sorry. Okay, so what I did on the quiz is the first two you had to do. The third one was a bonus. So you got an extra 10 points if you did the third one correctly. I was very particular about notation. All right, so I know it's the beginning of seeing summations and get everything in order. I included the examples to show you what proper notation should look like. So if you look at my solutions, I start with the limit. I carry the limit the entire way in my work the whole time until I get to the point where I take the limit, then it's no longer there. So when you do your work, I'm looking to see, like, obviously you're doing it correctly. I understand that you get it, but it's a matter of, just like when you write a paper, proper punctuation, things like that. Handwriting, you want to make sure that you're paying attention to those little details, all right? So if you have any questions on how I got your grade for the quiz, I'll be happy to talk to you about that. Just another thing about my office hours and stuff. On Mondays, I'm out of here. Right after class, I am on my bike. I'm gone, okay? Today, though, I'm not pressed for time. So if ever after class you need to talk to me on Wednesdays, we can chat for a while, all right? But on Mondays, I'm sorry if I'm short with you. I've got to get somewhere at 3 o'clock. So, FYI. Okay, so those are the solutions. I also handed to you this summary sheet. This is a kind of putting it all together, the relationship between areas, Riemann sums, and the definite integral. So I put it all on the board the other day, but now it's all formally written down. And the back of this page is really the thing I wanted you to focus on, where I have A equals, A equals, A equals, A equals, just to see how that sum eventually becomes a definite integral. Do we need more of these? You need a couple?
Oh, he does too.
Okay. Are there any others? Any extras? I have more here. Anyone need the solutions to the quiz? Okay, so just how those sums of all those rectangles, let it go to infinity, it eventually becomes that definite integral. All right, so you've got that now. And we're ready to begin unless there are any questions on homework or anything like that. Yes?
I got some questions about homework. Can I talk to you about that in class?
Sure.
Okay.
Yep. You mean like particular problems or, okay. Yeah, we can talk after class.
Okay.
All right. Okay, we are going to go through 5.2. Then we're going to do 5.3. And then we're going to jump to 5.5. So that's my goal today. So 5.2, most of this is going to sound familiar to you already. We pretty much have established now that definite integral. By the way, this section is called definite integral. So we've established that this definite integral right here represents the limit and goes to infinity. You have this written down already, so you don't need this. I'm just going to put it on the board. F x k, x sub k tilde delta x. And I'll just point out to you that in the book uses something other than x sub k tilde. They use x star sub I. So instead of indexing their summation with k's, k 1 to n, they use I equals 1 to n. And that indexing variable, k or I, it's a dummy variable. It can be anything. So you can always index a sum with any letter you want. The common ones are I, j, k. That's what we usually use to index a summation. So that's if you read through the book and you're like, what's this? It's that. Okay? And this right here, this definite integral, helps us to come up with a new definition, all right? It's what it means to be integrable. That's the word, integrable. So it's kind of like in Cal 1, we had functions and you would say, is it differentiable? Is that function differentiable? We can ask the question, is a function integrable? So this right here, this definite integral is equal to the limit of all those rectangles. If the limit exists, if this limit exists. So this is a big if, all right? I hope that you remember from Cal 1 that when you were studying limits, not every limit existed, right? Some limits did not exist. So maybe your teacher had you write like DNE for does not exist. Not every limit exists. Sometimes this limit doesn't exist, and that means it's not integrable. This area it's not possible to find, okay? So if this limit exists, we will say the function f is integrable. Integrable on that closed interval AB. So if that limit exists, then we say that the function is integrable on the closed interval AB. We already talked a little bit about the notation here, right? What's this sign called? Right here, what's this symbol called? The integral sign, okay? That's the integral sign. The A is called the lower limit of integration. The B is called the upper limit of integration. The function inside is called the integrand. And this right here, I said we'll focus more on it later, but it's called the differential. All right. So what about the answer to this? Like if you were to try and figure out the answer to an integral, right? If I ask you to figure out this definite integral, like if there is an answer, right? If there is an answer, it's usually a what? What do you think it is? What does it represent? Geometrically, what is it? Area, right? So it should be a what? A number, right? It's just a number. That's what I'm getting you to see. It's just, this is usually a number. Not always, but usually it is. Now, the reason why this is important, because a little bit later today we're going to be talking about not definite integrals, but what we call indefinite integrals. And what we'll do is we'll take off the limits of integration, and our answer is no longer a number, it's something else. So just remember, definite integrals are give us numbers as answers. Next thing. What is required of a function for us to be able to integrate it? Like, can you integrate any function out there? Well, there's some restrictions, and here they are. So what it takes to be integrable. So for a function to be integrable, it must be, the function must be continuous on a closed interval. What does continuous mean in layman's terms? What does it mean for a function to be continuous if you're just trying to explain it to like a third grader? No, maybe not a third grader, maybe like an eighth grader. Yeah, continuous without interrupt. You can draw it without picking up your pencil, basically. Well, that right there is a very strong condition, right? And think about it, drawing a function without picking up your pencil. So what about a function like this? What if you had a function that did this? It went like this, and then it jumped up and went like that. And I wanted you to look between here and here and find the area. Could you? I mean, isn't that a rectangle right there? And that's a rectangle right there, and you could get that area pretty easy. But that's not a continuous function. So I can't say it has to be continuous for us to be able to compute the area. It could be possible that there might be a break in the graph, but what it needs to be is that it has to have a finite number of breaks. So that's the next thing I'm going to write on this. F must be continuous on a closed interval with finite jump discontinuities. So it has to be smooth without picking up your pencil, or the most we could have is a bunch of jumps in it, but they have to be something you can count, finite, like 10 of them or 100 of them or 1,000 of them, but it can't be infinitely many jumps. Does that kind of make sense? All right, so those are the conditions that we need for integrability to exist. Now let's talk about a couple of the properties of integrals, of definite integrals. So properties. The first property that we have is the definite integral of the function f of x from a to b is equal to negative integral b to a f of x dx. So what is that property basically telling you? If you flip your limits of integration around, right? If instead of going from a to b, you go from b to a, it has the effect of changing everything by a sign. So that's important because later on you might have an integral where you want to change the limits of integration, flip them over, and if you do that, all you have to do is make sure that you change the integral by a sign. That's the first property. And I'm not going to prove these. The book goes through explanations of each one. I just want to put them on the board. The integral, from a to a of f of x dx equals, what do you think? 0. 0. So why would this be true? We might be able to understand this just with a picture, right? If I have a function here, here it is, and I want to look at the area underneath it between a and what? A? That's just that. It's just a single line, isn't it? What's the area of a line? Lines don't have areas, right? Lines don't have widths to them. So there is no area to that. Next property. The definite integral from a to b of a constant is equal to what, do you think? Of a constant. Maybe a picture. What does a constant function look like? Flat line, right? So let's say here's c, right? That's how far it would be, that's how high it would be. If it's a constant function, like if this was 4, it would just be flatlined at 4. And if I go from a to b, and I want to know the area, isn't it just the area of this rectangle? And what is the area of that rectangle? B minus a is the width of it, right? B minus a is how wide it is, times x, which is how high it is. You see that? So the answer to this is c times b minus a. We can show that another way, but in a little while we can verify that using the antiderivative and working it out. All right, what do you think the antiderivative, or the, definite integral of the constant 0 function is? Well, 0 is a constant, right? So it should follow this formula. So 0 times b minus a. So it should just be 0. See, this function has no height to it, right? So it should have no area underneath it. Any questions on these properties? They make sense? All right, next one. This is very much connected to derivatives. The definite integral of f of x plus or minus g of x dx. So if I have two functions being added or subtracted together, and I'm trying to figure out the area underneath them, then I'm allowed to separate it into two definite integrals and then add or subtract depending on what was here. If it was addition, I add. If it was subtraction, I subtract g of x dx. And that's just like the derivative, isn't it? Like back in Cal 1, if I said, hey, look, I have two functions, f plus g, and I said take the derivative, you would do derivative of f plus derivative of g, wouldn't you? Well, with the definite integral, which is connected to the antiderivative, it's the same thing. Antiderivative of these two added or subtracted is each one separately. All right. The definite integral of a constant times a function is equal to the constant times the definite integral of the function. So anytime you have a constant sitting next to a function and you're trying to find the definite integral, what can you basically do with that constant? Pull it out of the integral sign. And just remember, it'll multiply times whatever answer is there. So that's another property of integrals. How about this one? F of x times g of x dx. So instead of addition and subtraction, what if I have multiplication there? Do you think this? No. If this was the case, Cal 2 would not be hard. Cal 2 would be easy. It's the fact that this isn't true is what makes Cal 2 so difficult. And it's tied into the derivative again. Remember, what's the derivative of a product? Product rule, right? It's not just the derivative of each one. So when you try and reverse that, it doesn't reverse as clean either when we try and do it the other way around. So this is a huge mistake. If you do this on a test, this demonstrates a complete lack of understanding of the properties of definite integrals. So you don't want to make that mistake, okay? I hate putting wrong things on the board, but it's important, I think, that you see that it's not that simple. All right. A couple more properties, and then we'll be ready to move on. Division's the same thing. You can't just do division, all right? Break it into two. Doesn't work. So multiplication, division are going to be head scratchers for us. All right, next property. If our function f of x is greater than or equal to 0 on the interval ab, what does that mean? If I say a function is greater than or equal to 0 on an interval, then I mean that it's what? It's above or possibly touching the x-axis, right? Then if you try and find the area underneath that function, would you agree, or does it make sense that the area must then also be bigger than or equal to 0? If the function's above the x-axis, then we should have an area to it. Would this one make sense? Or does this make sense? If f of x is greater than or equal to g of x on an interval ab. So you have some function that's always bigger than or possibly equal to some other function. So if you graph them, the f is always above the g. How do you think the areas are related then? The area under F must be what? Greater than or equal to the area under G. That'll become an important thing when we get to the chapter on sequences and series. We'll have something called the integral test, and we'll use this property when we get to the integral test. And the last property. If little m is less than or equal to a function, which is less than or equal to capital M, I hate using the same letter, little m and big M, but that's what the book does, on an interval AB, then little m times b minus a is less than or equal to the definite integral. Everyone's got all these fancy ringers. Capital M b minus a That looks somewhat confusing, doesn't it? I'll draw a picture for this one. Hopefully when you see the picture, you'll kind of say, oh, that's not so bad. So let's talk about this. I'm saying, first of all, that you have some function on some closed interval, let's say from A to B, and that the function, I don't know, it starts somewhere, does something, I don't even know what it does, and then it comes back, let's say, over to here. Well, I'm going to raise this point up just a little bit, just so it's there. I'll just put it there. Then, would you agree that capital M is up here? In other words, there's a point, a value of M, where my function is always less than that capital M, right? And there's a smaller m that my function is never below, right? Then what does m times b minus a represent? What does this represent right here?
The highest area?
On this picture, what is it? It's b minus a is this width, right?
It's a rectangle.
So yeah, it's this little rectangle right here, isn't it? That rectangle? That right there is this, isn't it? That's b minus a times little m. And then capital M times b minus a is the large rectangle right here, isn't it? The whole thing. And doesn't it make sense that the area under our curve has to be smaller than the big rectangle, but larger than the small one? Would that make sense to you? No? Glazed looks.
Yes.
Does it or not? That area right here, just right here, is definitely smaller than the area under the entire curve all the way down. But the area under the curve all the way down is smaller than the biggest area, which is this. So it's just, it gives us bounds, restrictions on how big or small that integral can ever be. But what we always have to know is what's the biggest and smallest value our function is on that interval. Yes?
Is that big square just down to the little one, or is it the whole?
No, it's the whole thing. The big square, because its m goes from here to here. So it's the whole, this part right here is this times this. That one's just that times that. And then, of course, the true area of the curve is this stuff in here, all the way down.
That's why. Because each one consumes the next.
That's right. This little guy lives in the f function, and then that one.
Guys, because it looked like it was all.
I know. That's why I was asking if. All right. Those are our properties. Let's just keep them in mind. We'll be using them throughout the semester when we're evaluating definite integrals. Now, hold on a second. Okay. Now, this is the first time I've mentioned this. I have avoided, in everything I've ever done on the board, a situation where what I'm about to show you. When you look at a definite integral, it represents the area under a curve, right? That's what we've said. What I haven't alluded to is the fact that it's actually the net area. So if I take an example like, let's take f of x to be equal to sine of x. And let's look at it on the interval 0 to pi. Then if I draw that, we all know what a sine function looks. 2 pi is 1 period, right? This computation will result in 0 because it counts any area above the x-axis as plus, and anything below the x-axis will come out to be negative. So I know it doesn't, you might be saying, well, wait, areas can't be negative. But when we talk about the definite integral, areas above the x-axis are positive answers, areas below are negative. So since these are symmetric, they would cancel each other out, and your answer would be 0. Now let's try and connect that with the antiderivative that we've done already in a couple of examples. Last class, and we're going to spend almost all of today doing what I'm about to do right now. But last class we talked about it. If I want to go from 0 to 2 pi, sine x dx, I said last class that what we need to do is find an antiderivative of sine x, right? So hopefully you did some homework and you looked at things. What's the antiderivative of sine x? Negative cosine x. So it's negative, so the way I wrote it in class last time, I put negative cosine x, and then I put this line here, and I put the two limits of integration, 0 and 2 pi there. And this was just to keep things in order. And the next step would be to take 2 pi, plug it in. So I take equals, that equals negative cosine, plug in 2 pi, and then after you do that, subtract from that, plugging in 0 into this, right? So I subtract, plug in 0. Be careful, you have another negative. Negative cosine of 0. So capital F of B minus capital F of A. That's what I'm doing right now. Follow me? What is cosine of 2 pi? 1. Right? Cosine of 2 pi is 1. And then make it negative. So you get here negative 1. And then I have, let's see, what's cosine of 0? 1, make it negative, negative 1, subtract it, plus 1. So your answer is 0. So how would you figure out the area if you wanted to do that problem and you actually didn't want to count that as a negative value? Like if you just wanted to get this area and add them up, how could you do it?
To like change your greater than 0.
How do you mean?
I mean, you restricted the y-axis to greater than 0, but then that would kind of cut out the second half, right?
Yes, but I want to count that, but I just don't want to count it as negative. I want to count it as positive. So how do I count that? How can I get around that? What you would do is this. Is you would split your integral up, and you would go integral from 0 to pi of sine x dx. That would give you the area up to here, wouldn't it? And then you do another problem, and you go from pi to 2 pi of sine x dx. This answer is going to give you one answer, right? It's actually going to turn out, I believe, to be 1. And then this answer is going to turn out to be -1. But then you would say, wait a minute, I don't want to count it as a negative area. I want to count it as positive, right? So it would be 1 plus 1 instead. You would get 2. Does that make sense? We're going to deal with this more, but
Couldn't you change the second one from 2 pi?
you could flip it over. Yeah, you could change the limits of integration. Or you could just recognize, I know this part is below the x-axis, so whatever my answer is, I'm going to change the sign. Either way. Okay, so that's the first thing I want you to be careful of. Just because you get just because you do a definite integral and you know it's computing the area, any part of your graph that goes below the x-axis is counted negative, so it's going to offset anything that's above the x-axis. So you tell me, what would this be? If we keep that in our minds here, what would that be? Kind of got to know what x cubed looks like here to do this. X cubed looks like this, right? And at 1, you're at 1. Agreed? At -1, you're at -1. Ooh. And so the total area would be what? Would it be 0? It should be 0, right? Because it's symmetric, right? It's not perfectly symmetric, but this area here matches this area here. They're the same. And so the area from my function towards the x-axis, this negative part should cancel out this positive part, and it should be 0. Yes?
Does that apply anytime it's an odd function?
It has to be symmetric in odd, yes. I mean, you have to have the exact same thing on both sides, and it has to be odd means, well, even is this, right? Even is like that. So I'm going to say any odd polynomial, yes. That's what would happen. So this right here is not odd, that's even. So whatever area, let's say, would be over here, you would be doubling it, wouldn't you? Like whatever that is, doubles. But if it's odd, it goes this way, and they cancel. So yes. What was another question?
Could you
Yes.
take the derivative of it and just go from 0 to 1 and just double that?
Take the derivative. You mean, if I wanted the true area of this, are you talking about this one?
Yeah.
If I wanted the area of this and this together, and you're saying go from 0 to 1 and then multiply that times 2? Yes. But you have to first know that it's symmetric in that way. All right, so the big thing there is just to be careful that these definite integrals are giving you net areas and counting things below the x-axis is negative. And the last thing from this section that I want to talk about is kind of going back to our Riemann sums. When we had our Riemann sums, we were making these rectangles, right? Right? We made all these little rectangles in here. And didn't we always pick the right endpoint? Right? That was what we picked. It was the right endpoint, right endpoint, right endpoint, right endpoint. What if I would have said left endpoint instead? Would it have changed anything? So let me draw a little bit of a better picture. That picture's not so good. I'll do it with something very simple. How about just a line? Let's say from here to here, I want to create 3 rectangles and use the right endpoint for my Riemann sums. So I cut it into 3 equal rectangles, right? 3 equal widths. My first rectangle, if I pick the right endpoint, this is my first rectangle, isn't it? My second rectangle is this one, and my third one is this one. Yes? Now, if I do that same exact thing, but instead 3 rectangles but pick the left endpoint instead. So my first rectangle, instead of going to the right and going up and over, I go the left up and over. Then I'll be this, won't I? And then I pick that left point for the next one, go up and over, I get this. And then this one up and over, I get this. This is too much, isn't it? It was an overestimate. This one would be an underestimate, wouldn't it? Doesn't matter if you pick the left or the right. Or even better, could you do this? Break it into three rectangles, three equal rectangles, but instead of taking the left or the right, take the middle. So pick the point right in the middle, take it up, and create your rectangle based on the middle point instead. Take the middle point here, go up, base your rectangle each way on that. Do you all see the difference on this? And then take the middle point, go up, go left and right. Which of those seems like the best one? The middle, right? It turns out it doesn't matter. Why doesn't it matter? Why won't it matter at the end of the day when we're trying to find the true area? Why is it not going to matter if we pick left, right, or middle, or anything in between?
They're all approximate.
Still wrong.
They're all off, but there's something fundamental.
We put an infinite amount of rectangles.
That's it. When you let the number of rectangles go to infinity, what happens? They have to get more narrow, don't they? So it might make a big difference if you're just doing 3 rectangles. It'll make a huge difference. But if I do 1 billion rectangles, this becomes so small that the left, the right, and the middle are really almost the same point, right? And when I go to infinity, it is the same point. It's converging to the same exact thing. So it doesn't matter left, right, middle. But only because we let n go to infinity. So good. That's it. So the book, when the book does this, the book says x star I, and I used what? X tilde k? I told you x tilde k was the right endpoint, right? But in reality, x tilde k is any point you want to pick in that rectangle. Any one you want. It can be anything you want. Doesn't matter. All right? So I just wanted to point that out, that it doesn't have to be the right endpoint. We're done with 5.2. I don't have a homework assignment yet for 5.2. All right? It's not complete. I'm going to send an email out within the next 24 hours, probably. It's going to include your homework assignment, and it's going to include a take-home quiz. That'll be due on Monday. Okay, so you want to check your email. All right, we're ready for 5.3. Unless anyone has any questions. All right, 5.3, we're actually starting to get into the mechanical computational part of this class. Evaluating definite integrals. So it's time to find some antiderivatives. So we already know this. I've put this on the board before, but I'm putting it again. That the area underneath this curve, the net area underneath this curve between A and B, can be found by evaluating capital F at B and subtracting capital F at A. Here, capital F is what? The antiderivative. But we talked about antiderivatives, and didn't we say that if you give me a function, there's an infinite number of antiderivatives, right? So which one do I use? Well, this little theorem here says that where F is any antiderivative, where F, is any antiderivative. And so the one that we use, the most convenient one, is the one where C is 0. Remember, every antiderivative had plus C? Plus c? Well, why don't we use plus 0? This allows us to do it. I'm going to show you an example. It doesn't matter if you were to let c be 0 or 2. Everything, it's all going to give you the same answer. So let's do a problem. Let's find the antiderivative of, or the definite integral. Keep on saying antiderivative. Definite integral 1 to 2 of 4x cubed minus 3x squared plus 2x dx. So this is a polynomial function. The answer to this represents the net area below this curve, right? Between the intervals 1 and 2, or between the numbers 1 and 2. That's what it is geometrically. So the first thing I need to do is find a capital F, right? A capital F. So what's a capital F for this one here? Antiderivative. X to the 4th minus 3x cubed plus x squared plus any constant I want, right? Plus any constant I want. But I'm going to choose c to be 0.
Is it just x cubed?
Yeah, I don't know why I did that. Right? So the thing I just wrote on the board said I could use any c I want, right? Any c. I'm going to choose c to be 0, but let me show you if I leave it like this, the c won't matter, right? So the first thing I should do is I need to figure out what f of b is. What's f of b for us? F of 2? What would f of 2 be if we use this? So 2 to the 4th power is 16. Take away 2 to the 3rd is 8 plus 4 plus c, isn't it? What's that give you? 12 plus c? Now find f of a, which for us is f of 1. What's f of 1? 1 minus 1 plus c? Which is 1 plus c? Then what am I supposed to do? Subtract, right? I'm supposed to do, remember the formula was capital F of b minus capital F of a, right? So if I take capital F of b, which is 12 plus c, and I subtract from it, what? 1 plus c, what's going to happen to the c's? They're going to cancel, aren't they? And that will always happen no matter what c you ever pick. Right? No matter what I ever pick for any antiderivative, the c I have for this one is going to always go away with the c I have for this one. So why even put it there? Just use 0 as your c, because it has no effect on our answer. But what is our answer here? 11. All right, so that's just kind of showing you the different pieces. I'm going to redo this entire problem using the notation that I would expect you to use. All right, this is the way I would expect you to do this problem. What you do, take this integral, 4x cubed minus 3x squared plus 2x dx. The next line you write is the antiderivative with c being 0. So x to the 4th minus x cubed plus x squared plus nothing, right? Right? Plus c, but I'm going to use 0 for c. Then I'm going to put a line 1 to 2. So all this does is organizes your ideas here. To figure this out, I'm going to need the antiderivative, and I'm going to need to plug in 2 and subtract from that, plugging in 1. Equals, next line, I'm going to do two big sets of parentheses like this. This one here is capital F of B. This one's capital F of A. So capital F of B is 2 being plugged in there. So 16 minus 8 plus 4, and then plug in 1 over here, 1 minus 1 plus 1. This is the way most textbooks will do it, all right? You go from the definite integral to the antiderivative with these two limits of integration here, and then you go straight to the f of b minus f of a. And then our answer is what, 11? We're done. Okay, you all look like y'all are ready for something more challenging. That's the feeling I'm getting. So I will provide you with a little more of a challenge here. How about evaluating from 0 to 1 5x minus 5 raised to the x dx. So the first thing you have to do is figure out an antiderivative, right? An antiderivative of this. So what is the antiderivative of 5x?
5 halves x squared.
5 over 2x squared, or 5 halves x squared. So I'm hoping that you've done enough of the homework that you're comfortable with using the power rule for antiderivatives to get from here to here. Now, what's the antiderivative of 5 raised to the x? That's a different story.